Oh, good morning, everyone. I want to also thank the organizers both for organizing this meeting and for inviting me. My apologies for missing yesterday's discussion. I got a little summary of it from Neil over drinks, but I haven't been feeling 100% well, so I'm sitting down for this presentation, so my apologies to anybody in the back row. So Neil gave me this title, Gene Therapy Approaches for Aniridia. I modified it ever so slightly, and gene editing and nonsense suppression. I want to talk about both those approaches just a little bit. Therapy approaches for aniridia. So I have no financial interests for this presentation. And by far my focus of this talk is going to be announcing a new and much better mouse model for aniridia. Now, the mouse, I'll talk about this a little bit more at the end. The mouse will be available from JACS MMRRC in September 2024. It'll be alive for a few months in the fall, and then it will be cryopreserved at the JACS forever. I'm just going to say this is the last PAX6 mutant mouse I'm going to make for those who have been following my career, because I'm retiring my wet lab at the end of this year. So enjoy this one. It took me 5 years to make it, and it is really cool, if I may say so. Why is an excellent mouse model important? Basically, because organizations like the FDA ask you to cure the mouse first before getting permission to run a clinical trial. Now, I use the word cure very loosely. It could be simply something efficacious, something safe, maybe not a full cure, but nevertheless, they look at the mouse data very seriously before giving anybody permission to try something in patients. An example of this in our field is atalurin, where the mouse studies went really well, but the clinical trial a little bit less so. And I'm going to argue today that at least part of that problem was the mouse itself, that the mouse that we've all been using, or the mice that we've all been using in the last few years, are a bit suboptimal for today's therapy development. So here are 3 pictures from other people's work, a normal eye, oh, I have a pointer, one moment. An eye with iris hypoplasia, and then an end-stage eye with pannus. If I go, the mouse does very well. So a mouse's iris is the brown part here. The pupil is the little black circle in the middle. The iris goes all the way to the edge of the mouse's eye, in contrast to humans. Here's a hypoplastic iris with still quite a bit left, but still you can certainly see it. And here's an end stage with the pannus and the blood vessels growing over the surface of the cornea. So in that sense, our mice have been doing very well for us. But there are 3 problems that the new mouse is meant to address. First of all, therapies, and by this I mean both nonsense suppression and CRISPR-based therapies, bind DNA. Human DNA in the final use, not mouse DNA. So you really need a humanized mouse. And when I said I thought this might be the problem with atalurin, that drug doesn't just bind where the mutation is, it binds to the flanking sequences. And if the flanking sequences are mouse in the test, but human in the clinical trial, that could very much affect the effectiveness of the drug. So it worked well on mouse sequence. That would be my hypothesis, just to say. It's not known that's what went wrong, but a hypothesis that it worked well on mouse sequence. But it didn't work nearly as well on human sequence. If we humanize the mouse and do our testing in a humanized mouse, we'll know that it's not working well on the human sequence right away. and wouldn't even move forward to clinical trials. The exact, I'll leave that for a moment. The next thing that this mouse has is a reporter. Reporters are really important to understand mechanism and success of a therapy. And here the reporter is a flag tag. And then the third thing is genetic background. So we played a lot with genetic background. You're going to see some work from Neil's lab on a previous mouse that we made. And the idea of playing with genetic background is to make the mouse natural course of the mouse disease more similar to humans. So I'm going to go into each of these in a little bit more detail. Humanization for Adelerin, I kind of gave you that. It binds DNA. If the mouse itself has human DNA in it, if there's a problem with binding to the human DNA, we'll know right away. But interestingly, exactly the same argument is made for CRISPR-type approaches. So CRISPR is a gene editing approach where you literally change the base. And I'm going to show you data for the particular enzyme. It's called ABE8A, adenosine base editor version of CRISPR. And I'm going to show you that it works quite well on humanized DNA. How did we make this mouse? Well, basically, we made the mouse using CRISPR to then have a mouse to test CRISPR therapies. But the CRISPR, oops. Let's back up and get my pointer. So here's the piece of DNA that we put into the mouse embryo. It has a homology region on either end, about 100 bases, and then it has a region at exon 9, and red is human. And you can trick the mouse cell into doing homologous recombination in these end pieces and replacing the mouse exon 9 with the human exon 9. And that's exactly what we've done. So we've also added, so here we've made 2 mice. This is the control mouse in the sense that it's only humanized. The new mouse that I'm going to show you is humanized, plus it carries the most frequent mutation in aniridia, a single base pair mutation in aniridia in the humanized region. So if I show you some data from this mouse, it was really important to show that humanization alone did not give us an ocular phenotype. That would be a problem. But it didn't. We looked at it on our 2 favorite backgrounds, C57 Black 6 and 129. And in both cases, we could not distinguish a wild-type eye from a humanized mouse eye. And if we quantified this, you can see that there's no difference between the 2. I added a picture of the same mouse here so you can see what we were looking for if humanization had inactivated PAC6, for example. We would have expected an eye looking more like that. So humanization alone is not a problem. The PAC6 still works really well. And that's one of our lucky things with this particular gene. It's highly conserved. And even though the amino acids are identical in human and mouse in this exon, the DNA sequence is very different. Nevertheless, the 2 genomes work the same. Mice and human genomes are very similar to each other. So we added a reporter. I'm just going to go back for a second. With Adelerin and with CRISPR, you would like to know that the mutant allele or mutant chromosome is actually producing new PAC6. And especially in the nonsense-mediated field, that can be hard. Did we actually turn on the gene on the other chromosome? Or did we affect some kind of feedback loop, and it's really just more wild type that we're seeing? What we've done is we've added a flag tag to the 5' end of the protein. Let me go one more slide. Right there at the ATG. And that gives us two things. This is, for example, mice are heterozygote, just like humans are. There's a wild-type PAX6 making a wild-type protein. And here's our new mutant PAX6 with a flag tag. And when it makes a mutant protein, it is flag tagged. So there's no question if you use a nonsense suppression and you don't see any green tagged PAX6, then you haven't actually turned on the mutant gene. And the exact same thing is true for CRISPR. CRISPR is meant to turn on that otherwise defective gene. And if you don't see the PAX6, then you haven't turned it on. So we added, as I mentioned, oh, this is an earlier mouse that we had. I'm going to show you some data from it. We flag tagged this earlier mouse as well. We wanted to be sure that the flag tag itself did not cause trouble. And here's the data. So the Say is the traditional mouse. The Fay is the flag tagged mouse. So Say is small I. Fay is flag tagged small I, wild type, and then we actually added the flag tag to a wild type PAX6 as well. Because we wanted, just like the humanization, we wanted to convince ourselves that the tag itself is not going to cause an eye problem. And I think you can see in this very first pictures, here are the mutant eyes, and here are the normal looking eyes, and the flag tag did not cause any problems. We also wanted to be sure the flag tag worked, so that's stained. I'll just nip through this. There must be one more. There we go. Okay, so in this slide, she says, hesitating for a moment, the green is the flag tag. And so it should be exactly where PAX6 is. So red is PAX6, this is a retina. Green is flag tagged PAX6, and the two should co-label exactly. Oh, thank you so much. Last but definitely not least, we've been playing with genetic background. We want to make, oh, good typing, Beth. You can tell I haven't been feeling well. Like is not spelled that way. We wanted to slow down the course of the disease. So we've been using 3 different backgrounds. Black 6, that's the standard mouse that everybody uses for everything, really. It's like, well, only scientists will get this, but it's the E. coli of the mouse world. And then 129 would be kind of down there a little bit, not the most popular. But all the PAX6 mutants on Black 6 are very rapid. Now, for some experiments, that's very convenient. You see the phenotype of the PAX6 mutation right at birth. But for therapy, it's not convenient. You really want the time course to the development of, say, Panis to give you a therapeutic window before it happens, so that you can try to prevent it, for example. So it turns out that Black 6 is fastest, 129 is slowest, and a mixture of the two, B6, 129, is intermediate. In my lab, we're using the B6, 129 a lot. You're going to see data from Neil, from Dina, on the 129 background. But depending on your experiment now, you can choose your genetic background. So the final mouse is this. So this is the wild-type chromosome. Oh, she says, pointing with her finger. This is the wild-type chromosome. A normal ATG, a normal stop, making a normal protein. This is the chromosome we're going to play with in the mouse. First thing we did was add the flag tag. Second thing we did was humanize exon 9, but this time we added the human, high-frequency human mutation. It's a stop codon. So the mouse that's being very popular is called Say. It's actually a stop codon in exon 8. This is a stop codon in exon 9. And as far as we've studied it so far, it's a very new mouse, but we don't see any phenotypic difference. In both cases, I think the protein is never made and the RNA is degraded. I'm just going to wrap up by telling you these mice are going to be available at JAX MMRRC. If you're a mouse person, MMRRC is a mutant resource that has locations in different parts of the United States. The mice are actually going to be at the JAX location. So it's a little confusing. They call it MMRRC, but it's actually, physically, it's part of the JAX. They don't have details yet on their website, but they do have their numbers. And so this stock number, if you were going to order the mice from JAX, that's the number. And we bred it on the B6 background, and we bred it on the 129 background. So you'll get both of those things, and you can have whatever you want. If you let me know if you want this mouse, then I'm putting a list together, and I'll share it with JAX. And they're keeping it alive until they fill all the requests. And mice people know that taking it out of cryopreservation is very expensive. So you do, if you're interested in the mouse, it would be good to grab it while it's still alive and 4 paws on the ground, as they say, rather than having to pay to bring it out again. And that is everything I've got. Thank you very much.
Thank you very much, Elizabeth. I'm sure there are questions. I've got a couple, so Neil asked first. So.
We can take some questions. Thank you so much for this, and also for all your work in providing these really useful mouse models of the disease. And I think that's really a key factor in the future getting therapies to clinical trials. So really grateful for all your work in this area.
Thank you.
We're going to get that We're going to get that new mouse. Question is. So the PAX6 gene in the mouse is on chromosome 2. It's not like the human on 11. Does that have any consequences? No?
No, the mouse and human genomes are rearranged in chunks. And so the flanking genes in mouse are the same as the flanking genes in human. But they have rearranged their chromosomes. So it's And chromosomes are only numbered by size, not by homology. So a lot of chromosome 2 is actually 11. Oh, okay. But they call it 2 because it's the second biggest in mouse. Okay. So yes, that's not a concern.
That's not going to be a concern. Yeah. Okay, great.
Hi, thank you.
Hi.
And also personally, I would like to extend my thanks, like Neil said, for providing us with great tools for research.
Good.
All those years.
Yeah.
So my question is, why did you choose to humanize exon 9 and actually induce this stop codon in exon 9 rather than recreate the previous say with the stop codon at exon 8?
So although the same mutation is present in patients, it's very rare in patients. There's only, as far as I know, one family that has that mutation. Whereas the mutation that we added in exon 9 is the most prevalent of a rare disease, so it's not very prevalent, but it has occurred in multiple families. It's the most frequent. When we searched the databases, it was the most frequent. So that's why we did that. We thought that the development of a therapy would be most impactful with the most frequent mutation. But in the future, once you have something that's working, you would then begin to tweak it for all the different mutations, and you'd need to do this for all the different exons of PAX6. And we've certainly published our methodology, and although it took me 5 years the first time, it shouldn't take so long the next time, because that's exactly what's going to have to happen. If we have a good strategy for exon 9 mutation, we're going to have to humanize exon 8 and go for that one. Yeah. So that's why. It was a frequency game. Yeah.
And more relevant, I guess, like to the actual outcomes. So,
Right.
Yeah. Thank you.
Right.
Any other question from the Niels? Yeah. Well.
So this is probably an important question for many other people have this on their mind. So if we're thinking about gene therapy in the mouse and then gene therapy in the human. So what would you see as being sort of the optimal time and sort of delivery of that gene therapy for the eye to correct the PAX6 mutation?
So we've been working on that, and I do think the ABE, those base editors are the best. And the reason I think they're the best is because in a dominant disease, you want minimal impact on the wild type chromosome. And because the sequences are identical except for a single base, you can have some impact on the other chromosome with ordinary Cas9, for example. But the ABEs work differently and are much more specific to the mutant. So that's what I would recommend. But one of the challenges of the ABE is it's a very big enzyme. So we use adeno-associated virus, but because of the size of the enzyme right now, you have to use 2 viruses and have it sort of recombine with itself once it enters the cell. And people have shown that does happen, and we can get quite high frequency with GFP, for example, transduction of the retina or transduction of the cornea. We tried using lipid nanoparticles, and they don't have the size limit, and that's another way to go for the cornea. But I think the field is improving in making the ABE enzyme smaller, in which case it'll be easier to work with. So certainly right now, our model is intravitreal injection of either lipid nanoparticles or virus to deliver the gene therapy either to the retina or the cornea. Yeah. At what age? Earlier the better is what we would like. The cornea, we also do intrastromal injection into the cornea. That one, the mouse really has to be at least 8 weeks old. It's just too small until then. Intravitreal, you can do much younger. We would do 3 weeks. That would be the youngest that we've been successful. The thing, that's a thing where humans have an advantage. You'll be able to go younger in a human because the eye is so much bigger. It's a limitation of the mouse that even putting a microliter of virus in a 3-week-old eye is a lot, whereas a microliter into a young eye, human eye, is nothing. So mouse does not mimic the human situation. If we can do it, if we can kind of get away with it in mouse, it'll be easier in human from that point of view. Yeah.
Sorry, I have a question. Talking about the now a potentially human application, how? I mean, it's difficult for me to see like an in vivo approach, or I mean, not difficult, more difficult to see an in vivo approach. And I was wondering whether an approach based on taking the limbal stem cells in from a biopsy, growing up them in vitro, and then modify them, and then putting them back onto the patient would be a sort of approach that you would suggest.
Yes. So in the field of gene therapy, ex vivo approaches almost always are used first because they're safer. You can spend a lot of time characterizing those cells before you put them back into the patient. In vivo is usually the long-term goal because one and done, you do your injection and you're finished kind of thing. So I would see an intermediate step doing exactly that. And you have no rejection problems, of course, because you've taken the patient's own cells, corrected the mutation, and put them back in. I don't know anybody who's tried doing that with a mouse yet, but I think that is a great idea. Yeah.
Why do you say intermediate? Because in the long term, you would prefer like an eye drop or something also for human applications.
Yes, I do consider that intermediate because I don't think the disease is a stem cell only disease. So I think correcting the stem cells and putting them back is going to have a limited therapeutic effect. What I'd really like to do is put PAX6 back in every cell of the eye that should have PAX6. And I can only see that with an in vivo approach. Yeah.
Okay. Somebody agreed with your view, clearly. Okay, any other question? I mean, you got the chance to talk to Elizabeth, so...
I'll be around, yes. I'll be around.
If not, I think we're going to move to the next presentation. And we thank Elizabeth for